So the last case I want to discuss deals with free expansion. And so this is going to be different from the first two cases because in this system we're not dealing with any sort of piston cylinder expansion or compression. Instead, what the premise is in the initial state we have some sort of system, it's adiabatic, and we have a gas separated on one side of the compartment from another side of the compartment that's completely under vacuum. So there's no molecules in there, it's just empty space. All right, and so that's the initial state. And then what we do is then we somehow, the compartment or the wall that's separating the two compartments, we somehow like poke a hole in it, right? Or we open it up. And by opening it up, that allows the gas to move from one side of the compartment to the other compartment as well. So that eventually in state 2, the gas fills up the entire container. Okay? So that's what we mean by free expansion. And so for this sort of scenario, the first question that we need to immediately ask ourselves is, what is the mechanical work that is going on? So what I want you to do is to pause the video here and just sort of kind of think to yourself what you think the value of the mechanical work will be. It turns out that whenever we have free expansion, the mechanical work that occurs in the system, even though the gas is expanding, the mechanical work that occurs is exactly equal to 0. Okay? And the reason for that is because the expansion of the gas is not acting against any sort of force. So it does not act against a force. Okay? All right, and so to be more quantitative, or at least give a more precise answer for why the mechanical work is 0, let's think about what the work exerted by the vacuum is as the gas is expanding in state 2. Okay? And so with the vacuum, the force exerted by the vacuum is equal to the pressure of a vacuum times whatever area that it's acting on. AP with just some sort of area. All right? And so we're dealing with a vacuum, and so by definition, the pressure of a vacuum is equal to 0. All right? And so that means the force exerted by the vacuum is also equal to 0. All right, so the force of the vacuum is 0. When this gas is expanding, that force exerted by the gas has to be acting against the force of the vacuum, right? In order for it to expand. But like we just said, the force of the vacuum is equal to 0. And so that means that from a force balance argument, that the force exerted by the gas as it's expanding also has to be equal to 0. And thus, if we go to our definition of dW mechanical, which is equal to the negative of force gas dx, if we plug in our answer for F gas, what we get is that the mechanical work is also equal to 0. Okay? And so during a free expansion, when the gas expands against a vacuum, that means that its mechanical work that it's exerting is equal to 0. With that knowledge in hand, let's go to our energy balance to see if we could get any more insight into the system. So from our energy balance, we know du plus dek plus dep is equal to dq plus dw. Assume changes in kinetic and potential energy are 0. From our argument up above, we know dW is 0. And also, as I said, this system is adiabatic, right? There's no heat coming into or out of the system. So this is also going to be 0. So what we get in the end is that the infinitesimal change in the internal energy, or du, that's also going to be 0 as well. And as such, the internal energy of state 2 is going to be equal to the internal energy of state 1. All right? So that's what happens in free expansion. And we could extend this argument even further, because let's say we're dealing with an ideal gas. If we're dealing with an ideal gas, we then know that the internal energy is only going to be a function of temperature. Now, that's the only thing that will be able to change it. And so, if our internal energies are the same in state 1 and state 2, then for an ideal gas, what that means is that the temperature of state 2 is also going to be equal to the temperature of state 1. And so overall, whenever we're dealing with this sort of free expansion sort of scenario, what we actually have is an isothermal process. So from an energy balance perspective, this free expansion process is very simple. But later on in the course, we'll kind of look at, even though the energy of the system isn't changing, there is some sort of thermodynamic driving force that's causing the gas to go from its tiny compartment all the way to the full compartment.